Hello there, my name's Gary Sims and this is Gary Explains. Now today we're going to be looking at Piccolo OS, the internals of Piccolo OS, which is my demonstration multitasking operating system for the Raspberry Pi Pico microcontroller board. The idea being to teach you how you can write your own multitasking operating system for any microcontroller board based on a Cortex-M microcontroller. Okay, if you want to find out more, please let me explain. Okay, so really there are two prerequisite videos to this one. The first is how to use C and C++ on the Raspberry Pi Pico. The second is my video on context switching, where I talk about the whole idea of how you run tasks in parallel. And over on that video, I actually do a quick demo of Piccolo OS running. Now this is going to be quite a deep video. It might actually be quite long. I thought about splitting it up, but let's just do it in one big chunk. Now, at one point, I will say this is a cut-off point for some people who just want to go ahead and just go and test it out, and I'm not really interested in the really fine details. So when that slide comes up, that's your cue to go off and try it. But I really do recommend you stick through right to the end, because I cover absolutely everything about interrupts and stacks and process stacks and the main stack pointer and how you swap between the process, all there, but you just need to stick through, okay? So sit down and get a cup of coffee, a cup of tea, whatever is your favorite drink, and let's get cracking. Okay, so what is Piccolo OS? It's a very small multitasking OS for the Raspberry Pi Pico. Of course, Raspberry Pi Pico is a microcontroller board. It's designed primarily as a teaching tool, teach you the fundamentals so that you can write your own multitasking OS, not only for the Raspberry Pi Pico, but as I said, also for other Cortex-M type boards. It demonstrates the fundamentals that you need of both how the multitasking OS works and about the Cortex-M series of CPUs. And what about limitations? Well, there are many more than are listed here. This really is a very simple, small multitasking OS that shows you the principles. So there's no per task memory, doesn't support the other core that you find on the Raspberry Pi Pico. There are no advanced OS features like queues and mutexes or a file system or networking or so on and so on. And it is cooperative, not preemptive, and we'll talk more about that in a moment. So cooperative versus preemptive, why is that? Well, the fundamentals are basically the same. If you go back to my context switching video, this is basically the same things happen between these two modes. In a cooperative multitasking OS, the task decides when to yield control back to the OS. So there is a command called Piccolo yield, which says, okay, you can now go off and process the other kind of tasks that are running, or control is taken away when a system call is made. So for example, there's a Piccolo sleep command which will automatically take away control, and you can wrap other functions like turning on and off a GPIO, doing stuff to the serial port. These could all be wrapped up so that every time you do them, it goes off and does its cooperative stuff. In a preemptive multitasking OS, control is taken away from the task based on time, normally via a timer interrupt which fires every few milliseconds, and it doesn't matter what the task is doing, it kind of just switches over to the next one. A cooperative multitasking OS is easier to understand, while at the same time laying the foundation that you need for a full preemptive multitasking OS. See the README file in the GitHub for more information. Okay, talking of GitHub, where is the source? There it is, github.com/Gary Explains. Once you get there, drill down to examples, Raspberry Pi Pico, Piccolo OS. It's licensed under a 3-clause BSD license, which basically means you can do whatever you like, but you do need to retain the copyright. And as I say that, I would like to acknowledge the additional copyright holders for various snippets and ideas that I have been able to use while making Piccolo OS, and I give a full list and full credit to them in the source code and, of course, in the README file. So let's just start with this snapshot of the main process I've shown several times over the last few videos. So what we've got here at the beginning, Piccolo init, that initializes the stuff that you need. We'll talk about all these things in detail in a moment. We then print out something saying, hey, we're running. We then create 3 tasks, and in my demo it was one LED flashing at one rate, a second LED flashing at a different rate, and the third one was checking prime numbers and printing them out on the serial port. And then once all your tasks are created, you then call Piccolo start, which is an infinite loop, so it never returns from this. This return here is never going to happen, and this goes round and round and round, running these 3 tasks. So what would a task look like? If you notice here, task one func. And if you go back to the previous slide, you can see here task one function. Func, that is what is passed in. So this one, what does it do? It initializes the GPIO because we're going to be playing with an LED, sets it to be an output, and then you have a loop here which goes round and round and round and round. You turn it on and you turn it off, and in between you sleep. And as I said earlier, the sleep command here automatically has a yield in it, so that while it's waiting for this 1000 milliseconds, other things are allowed to go on and happen on the rest of the system. So that's what it does, just goes round and round and round, switching LED on and off. The other ones are very, very similar, different rates. And in here also you can insert some code for, working out prime numbers, but this is basically what you have to do. Do your initialization and then stick in a loop doing something. So what are the files you're going to find over on the GitHub? Piccolo OS demo is where you find the main function, along with these three task functions. So if you were writing a program yourself that you wanted to use the Piccolo OS, you would just change this file to do all the stuff that you wanted to do. These other ones, you would leave them as they are because they're already working as they are. If you want to get into the internals, Piccolo OS contains Piccolo init, Piccolo create task, Piccolo start, and Piccolo sleep, which we've just talked about, and we will dive into all of these a bit deeper in this video. There's a header file, and then there's context-switch.s, which is some Arm Cortex-M0 assembly code. This is where things do get a bit interesting, and in here you've got the an interrupt handler, that's the SV call here. You've got Piccolo pre-switch, and you've got Piccolo yield, and we'll talk all about those in a minute. So what do the functions do? Piccolo init calls the Pico SDK SDIO init all, and then switches the CPU to handler mode. If you remember, we talked about this in the context switching video. Handler mode and thread mode. In handler mode, it's using the main stack, and it's what you do to handle interrupts, and you get there via an interrupt. And then thread mode is the task that runs. Create task, used to create a task and switch to it via Piccolo pre-switch, was the function that we saw defined there in the ARM assembly code. We will look at this. Piccolo start, as I said, is the infinite loop that selects the next task and runs it, again using Piccolo pre-switch. We will look at that. The yield causes the exception, which is handled by the ISR SV call. So that's the interrupt handler, and so yield basically says let's cause an exception, let's cause an interrupt, and then that gives us a chance to swap to a different task. And then these last two here are the ones that we found inside of the assembly code. Switches from task to kernel, and the other one switches from kernel to task. So depends on whether you're going from the main OS to one of the tasks, or from the task back to the main OS, depends on which one of those two calls is used. Okay, now that's what I was saying. You can stop here if you want. Now you've had an overview of how the functions are, what they are, what you need to call. You know where the GitHub is. You know what the files are. If you just want to test it out and you don't want to go to a deep dive, then now will be a good time to bail out. Go to the GitHub, get the code and give it a try. And there are lots of details. I spent quite a while writing a significantly big README file as a reference guide if you need it. Of course, I would recommend that you stick around because I'm now going to deeper dive into some of these things. And I can tell you, rather than you having to read the README file as a bit of light reading at night time, so please stay around. But if you have to go, bye thanks for watching, but let's carry on. So how is a task created? So let's say we want to create task 1. Okay, so task 1 is created by calling Piccolo create task. We saw that already in the main program. So in Piccolo OS create task, and notice the underbar here, this is basically just a function that gets called from this higher level one, and the underbar here is kind of to demonstrate this an internal function. What it does, it creates a new stack. Now remember, with context switching, it's all about stacks. Which stack am I using? Because on the stack, you've got a copy of the registers so that you can carry on exactly as you were before you got switched away from. So it creates the new stack. And then we call Piccolo pre-switch, which is in the assembly code, and you pass in the stack. So this basically says, I want you to switch from kernel mode to the task using this stack. And what does it do? It saves the kernel state onto the main stack. Notice it is the main stack. And then the task state is restored from the stack that we just created here. So when we created this stack, and we'll look at the code for this in a minute, you actually need to put some things on it to mimic the fact that it got here by an interrupt call that the hardware did. And we'll look at that in a moment. Now, once that has happened, you then set the process stack pointer, the PSP, from R0, and this we'll be looking at R0 register 0. We'll look at some Cortex-M code in a minute, and then you jump to the return address, which is actually FFFFFFFD, And if you remember from the last video, that actually tells the CPU that this is the end of an interrupt handler. This is the end of running in handler mode. And you want to switch back to thread mode using the stack that's actually the stack for task number 1. So this is a really neat way of creating a fake stack, the mimics that you got here from the interrupt handler. You then return from the interrupt handler using this special return code, and then it uses the rest of that stack to run the thing. So task 1 now runs, and it will keep going until Piccolo yield is called. As we saw in our demo there, Piccolo yield is called from the sleep command as well. Now, when Piccolo yield is actually called, it intentionally causes an interrupt to occur, forces an interrupt, and that will be handled by ISR-SV call. Now, when an interrupt happens, the hardware automatically saves some of the registers on the stack and then jumps to the interrupt handler. Okay, so the interrupt handler is ISV-SV call, and that's predefined by the Piccolo SDK, so that when this type of interrupt is arrived, it will run this code. And what that code then does, it saves the state of task 1, because we were in task 1, it was running away nicely. We save the state of task 1 into its process stack. Then we restore the kernel state. Now, where did we see that the kernel state was saved? Up here, 3A. It saves the kernel state on the main stack. So now it restores the kernel state from the main stack and returns to the kernel using the return address that was saved in 3A, as I said here. After the interrupt processing, the processing continues all the way back to main, where we can then create a second task and a third task and a fifth task, whatever it is you want to do. And so that's how you've done it. We've switched to the task switched back, and we did that doing the stack stuff, putting stuff on the stack and restoring it. And that's context switching, as we discussed in the other video. So here's the flow of functions, just to kind of get rid of all those words. You're in main, you create a task, that calls Piccolo pre-switch, which means you end up running in thread mode. This here down the left-hand side, look at this. Handler mode, handler mode, handler mode, thread mode, thread mode. So it just tells you what mode the CPU is. You're in thread mode, running it using its own process stack. You're running task 1. At some point, Piccolo yield is called, which forces an interrupt to happen, which means you go back into handler mode, because interrupts are handled in handler mode. So you get into this interrupt handler, and then that actually, because you restore the kernel stack, gets you back up here into main, where you can carry on doing things. So that's the sequence of events, and we're going to see this sequence of events several times now through this video. So Piccolo pre-switch, and then the ISR SV call function. These two are important. Switching from the kernel to the task, switching from the task to the kernel. Right, now let's look at some actual C code. Let's define something here. Piccolo OS stack size. How big is the stack for each task? Well, let's call it 256. What's the maximum number of tasks? I've said 3. Of course, you could do more, 5, 10. There will be a limit, of course, based on the amount of space, RAM space there is inside of your Piccolo. 3, 5, they shouldn't be a problem for any of those things. We define this structure, which is the Piccolo OS internals. What's he got? He's basically got a set of stacks, and that's the stack size multiplied by the number of tasks, so 3 times 256, that's how big that is. And then there's a set of integers which tells you about each of the actual running tasks. And then there's a task count, because at some point we may have only created 2 tasks, and then it tells you what the current task is. So all of these structures are used, and we'll look at those in a minute. Basically, the most important one there is this stack, because as we said, context switching is all about stack. So we create this stack that is used by each of the tasks as they are created. Okay, so here is the create task code at the high level. First thing it does, it says if there is already 3 tasks created, in our case, the OS task limit, then return with a -1 because it failed, okay? If it, then what I do is I set this integer here, TC, just for readability, because otherwise I have to put in here Piccolo context task count in this next line down here, which makes it a bit more hard to read. But basically, this tells us what the current task is that we're looking at. Which is always the task count, of course. So what we do is we say the task, so we're creating the pointer for the task that gets returned, from Piccolo OS create. We call Piccolo OS create, and here's the important thing, passing in this stack. There it is. There's the stack that we've already used. Which one? The one that's the current number of the task. And what do we have? Pointed to the task function that's passed in here. So in this case, task1 func. So that gets passed in here. So that's the task that's going to run. What does the internal Piccolo OS create task do? Well, it creates an initial process stack, which we're going to call PSP1. not PlayStation Portable 1, but PSP 1, that mimics the stack from an actual interrupt call. So here's a picture of the stack. Now, on the stack here, we've got R0, R3, LR, and PC. Those are the things that get saved by the hardware automatically when it knows there's been an interrupt. And that's because it wants to go and handle the interrupt. The interrupt handler can then freely use R0 to R3, and then it can return to where it came from very easily. We also then put on the stack R4 to R12 so that we actually save all of the registers. So now the complete register states are saved, and also we save LR, which is actually going to be this special FFFFFFFD, so that it knows how to return out of an exception. And then once you have the stacks, we then go ahead and call Piccolo pre-switch, which goes ahead and does the task switching around between the main stack and the process stack, and we'll look at that in a moment. So here's a bit of C code. We've got this stack. Remember, it was up to 256 integers long, and what we do here is that because we need to mimic the stack from this previous slide, these things in here, this is the actual stack as an array. And the key thing to note here is that the LR here has to be FFD, and that this one here, the PC, where it came from when it had the exception, needs to be set to our function that we want to run. These two things are really important. So 15 and 8, and we'll look at that now in the C code. The rest of them actually can be anything they like, because the first time you create a task, it doesn't matter what's in there because it's the first time it's ever run, just dummy memory. Of course, later on when we're doing actual switching, all of these bits will actually be full of the actual registers that the compiler and the assembly language, all that have done to create whatever function it is that you're running. Okay, so let's have a look at underbar Piccolo OS create task. Notice this, look, 8 is FFFFFD, because that looks down here to find as Piccolo OS thread PSP is that, so that's defined in there. 15 gets to define to be the pointer to the task function, so task 1 func in our case. And then finally, as I said in that previous slide up here, you've got to set this to the thumb bit. The thumb bit is just a thing about how the ARM processors can run in different modes, and it runs in thumb mode. We've not really touched about that, don't worry about it, it never changes, it's just set to that. So the last thing it does, as you notice here, is it calls Piccolo pre-switch. That's ARM assembly code. So let's have a look at that. Well, what does it do? Here's my diagrams again. It saves the kernel state onto the main stack. Remember, it's all about stacks. Main stack. So we've got R4 to R12 is saved onto the stack. Then it loads the registers for task 1 from the stack that we just created. So this C code here created this stack with these different things in it that we've talked about. We now actually roll that back off the stack and actually set the registers to those things. We set the PSP register, which is how in Arm Cortex code you say, use this stack now, please. Don't use the main stack, use the process stack. And then we return to FFFFFFD, which causes the CPU to exit the interrupt handler. And then it will, having taken this top bit off the stack, we're now left with this bottom bit, which is actually the same as what would have happened if you called an actual interrupt. Oh, I recognise this is a nice exception frame. And so what it does is it returns to the PC here, which is what? Well, we've actually defined that to be the pointer to our task. So by slipping in that address there, when the exception returns, it returns to the place we told it to, which is task 1. So we've swapped stacks and told it where to return to. These are the fundamentals of context switching. And so let's have a look at a bit of the ARM assembly code. Here's a picture of our stack so that we can remember it. What do? We take this special register and we save it into R12. R12 and IP are the same thing in ARM language, can be a bit confusing. Then we use stack terminology, push R4, R5, R6, R7 and the return address onto the stack. Then we also want to save R8, R9, R10, R11 and R12. Now on the Cortex-M0 you can't do a push directly of R8, so you have to move it into R1 and then push that. So all we do here is basically move R8 through to R12 into R1 through to R5 and then push those on the stack. So you see at the bottom here we've got push R1, R2, R3, R4, R5. So that way we've managed to save all these things, which is why the stack is not in the same order. Look here. You've got 7, 6, 5, 4, and then 12, 11, 10, 8, 9. That's because we're doing it in 2 halves. As long as we know the order of it, it doesn't matter because we know how to unroll it. We know how to take things off. But on other Cortex-M processors, you can actually just do R through R4 through to R12 in one go, but not on the Cortex-M0. This is getting into the details, but this would work also on other Cortex processors without any problem. And then once it's saved that stuff, it then loads the user state, and that's the opposite what we just done. So you push the kernel, and then you bring in the task, and this is using the stack that we just created with that pointer to the stack function. Now, load from memory, increment afterwards. It's kind of like load from this R0 space and then move the address on one. Okay, so this does the opposite. So R0 points here. It loads in R8, R9, R10, R11, which actually then you have to copy over to R8, R9, R10, because on the Cortex-M0 you can't actually use these ones. We have to use R4 to R7. Okay, and then it does the same thing for the real R4 to R7. And finally, you do a branch to this return address. This is a special register in ARM, this return address, and that actually causes it to jump to FFFFFFD, which causes it to say, I'm at the end of an exception, and then it unpacks the next frame below it. And so now task 1 is running because we've got that return address on the stack there. So we trick the CPU into returning to our own place, and it will run until Piccolo yield comes along, which is called in Piccolo sleep. And what does it do? Piccolo yield intentionally forces an interrupt to occur. So the hardware, saved by the hardware, will automatically put these things on to the stack. Which stack? PSP1, the process stack. So the main stack, which has the kernel state in, is not touched. It's all nice and pristine, doing whatever it likes. This then forces, now of course you recognize this picture because we just created one of these ourselves when we created the task. And then ISR SV call actually saves R4 to R12 using exactly the same techniques as we've just looked at. And now once it's done that, the state of task 1 in the middle of flashing its LED has been saved. So let's look at the code. Stack pointer gets moved into R0. We then need to save R4, I5, R6 and R7 first because we've got this whole stack order problem that you can't push R8 onto the stack with a Cortex-M0 processor. And then also the Cortex-M processor is missing some commands, so we've only got the store increment after. Now if you notice, we did a load with increment after. You can't do a store and then the opposite would be a load increment decrement, or you do the opposite, you store and then decrement, because we're going in two different directions, but you can't do that on the Cortex-M0. So what we have to do is store it and then start taking numbers off from the pointer ourselves. We start taking 4, 16, 32, because we're jumping around the stack ourselves. Okay, so that's a limitation of the Cortex-M0 processor. But basically, if you look at it, if you do study it line by line, we're saving R4, R5, R6, all the way up to R11, and we're moving the R0, which is the stack pointer, to make sure it's pointing to the right place. Because there's a limitation, you've only got this one command, storing and then increment the address on the Cortex-M0 and M0 Plus. Okay, you can look up those commands, but basically just notice here that it's this trick again. R8, R9, we're putting them to R4, R5, then we're storing them. Look down there, we're pushing them onto our stack, which is really R0. Then once it's actually pushed all that stuff onto the stack, remember the main stack from earlier on? What have we got on the main stack? Well, we pushed this with the push command onto the main stack, R4 all the way through to R12. So now it says, well, okay, let's bring those back so they were in exactly the same state as they were when we left. And then we're able to switch back to our main stack, to the kernel, and it carries on exactly as it left off. But the key point here is that execution continues in handler mode. We're still in the interrupt. Even when we switch back now into the main or back into Piccolo OS start, we're still actually in handler mode, which means we're running as a handler, which is why when we switch back to the task, that's when we use the 0xFFFFFFD, because we're saying now is the end of the interrupt, and the interrupt was caused here when we yielded away from the other one. This really is the key to understanding how this works, that you've got to understand that we switch away with an interrupt and we end the interrupt when we switch back to the task. And here's the code, much simpler. Pop, because it's push and pop off the stack, pop R1, R2, R3, R4, R5, and then we want to do the same for the real R4, R5, R6, R7, because of course we were using, because you can't push and pop R8, for example, as I said earlier, on the Cortex-M0, so we just use 1 through to 5 as a dummy. And then finally you pop off, here's the important thing, you pop off the program counter, which means we go back to the kernel, because that's what we saved on there, so we're forcing it to jump back into main, the main code, or Piccolo OS start, wherever you are, and it just goes back to where it was. So we've switched away from the kernel, and now we've switched back to it again. Now, once all the tasks have been created, that was just showing how to create one task. You could repeat that, okay? You then just call Piccolo start. Sorry, I called it Piccolo OS start earlier on. Piccolo start, which basically goes around in an infinite loop, and it picks the next task that it wants to run. And remember, this is the task that got saved. It got saved in ISR SV call. This part got saved by the hardware. This part we pushed onto the stack ourselves. I showed you the assembly code that did that. So now when you switch back to it, you can do exactly the opposite. You can pull all that stuff off. You can say to the CPU, hey, we've come to the end of the exception handling. It will then jump to this frame and carry on using these registers at this program counter, and we've switched back to task 1. So it's all about stacks and switching between them, as I've said, I think about like 50 times until now. And so Piccolo pre-switch saves the kernel state, as we've just said, and then loads the registers from task 1 that I just showed you in this previous slide. So it's again the same thing. You just switch from one to the other, and then since the return address is FFFD, then it causes the CPU to exit the handler and return to thread mode. And because the hardware is the one that's doing the restoring of R0 to R3, by the time you get back to the process stack 1 for task 1 stack is empty. Or if it's not empty, it's in the state that it was before we left, if the program itself was actually putting things on and off the stack, which is often what happens. But we added things on when we switched away, and then we've taken them all off when we came back. And so now the stack is as it was, and all the registers as they were, and it can carry on running. It will keep on running until Piccolo yield is called again, which will cause an interrupt. So it then switches back into the kernel, and the whole thing just goes round and round and round. And so if you look at that from kind of just the functions, Piccolo start causes Piccolo pre-switch. You're then inside task 1 in the thread mode. That will keep running until Piccolo yield is called. That will go into the interrupt handler, and then ultimately that goes back into Piccolo start, and Piccolo start picks the next task, and you just go round and round. Task 2 would be here, task 3, and this is what it is. So again, it's switching away from the kernel to the task, and from the task to the kernel. One's done in Piccolo pre-switch, the other's done in the interrupt handler, and that's the fundamental. Now, I've said all that. Now, I've written quite a lot of documentation in the README file. Looks like there's 17 pages here, including some resource links and things like that. Okay, I've got all the stack diagrams. You can see them all there. And I go into detail about exactly which function is called and when. So if you need a reference guide for everything I've just said, then go ahead and have a look at the README file. Okay, so that's about it. Now, let's just talk quickly in closing about contributing. I would like to keep the basic version of Piccolo OS intact as it is, as a learning tool, so that people can watch this video, they can find that source code there, and then it all matches up. I don't plan on expanding that, including to add preemptive multitasking. However, if there is an interest, then a V2 could be started, which expands on V1 and includes things like preemptive multitasking, as well as other things like mutexes, queues, and so on. If that does happen, then I will create a V2 repo and start accepting pull requests. It may not happen. I don't know whether people are going to be interested in this or not. If it does, we will. If we don't, it's fine. This video is here and talks about V1. Of course, having said that, please feel free to fork and continue and work on your own little version on the Raspberry Pi Pico, because this is here for you to teach how to do it. It's licensed under a 3-clause BSD license. Basically, means you just need to keep the copyright notice there and then do whatever you like with it. Okay, so that's it. I really hope you enjoyed this video. I won't keep you any longer. I think it's been long enough. If you did enjoy it, please do give it a thumbs up. Don't forget to subscribe. Okay, that's it. I'll see you in the next one.